Alright, in today's lesson, we're going to talk about lesson number 5, percentage yield and percentage purity. Now, percentage yield and percentage purity are very important because the big idea here is in a reaction, we do not always attain the full amount we calculated, and thus we have a percentage yield. In addition, our product's not always 100% pure, so we're also going to have to deal with what we call percentage purity. So what are percentage yield and percentage purity? Well, a couple things that we kind of made an assumption of when we first started doing our stoichiometry was we assumed all reactions always formed these two things: 100% product and 100% pure. Now, some of you might have watched TV show Breaking Bad before, and Breaking Bad demonstrated purity in a very important way, talking about how the drugs that Walter White was making was pretty close to 100% purity. But that is not always the case. The reason why we don't really obtain both 100% product or 100% purity is because we run into issues when we are creating our products. And this is so not the case. And this is due to we sometimes will get what we call impure products, aka we're going to get products that we don't want. That's the first thing. We might not have measured properly, so we measure improperly. That's another one. Recovery is difficult. Say, for example, you create something, but you don't get all of it. So recovery of product is difficult. Say, for example, you made cookies and you couldn't get all the batter out of the mixing bowl. The last one is just human errors. There are human errors involved. So that is why we have percentage yield and percentage purity. In a reaction, any experiment we usually do, we're going to not ever really get 100% product or 100% purity. So how do we find percentage yield or percentage purity? Well, the big thing is they're actually calculated the same way. First of all, they both have a formula. Percentage yield is calculated as the actual yield over your theoretical yield. Now, what do these two words mean? Well, what percentage you get is based on how much you get from experiment, and that is your actual yield, while the theoretical yield is from calculation. So this is from your experiment, and this is from your calculation. Now, as you can see, you really just have three variables in this equation. You have your percentage, you have the actual yield, and you have a theoretical yield. In order to solve any of these, you always will need two of the other. So, how do we solve for this? Well, the first step is we solve any calculation using stoichiometry. So we still do any calculation we have always done using stoichiometry. But here's a little strategy. When you're calculating stoichiometry and you're converting and you're given, if given a reactant to start off with, and you convert it to a product using stoichiometry, you just solve for the theoretical yield. And if given the product and you convert it using stoichiometry to the reactant, you just solved for your actual yield. And we're going to practice this when we get to examples, questions of it. Okay, how do we solve for percentage purity then? Is it similar to percentage yield? And the answer is yes. It's exactly the same, just different terms. Because now if we talk about percentage purity, this is equal to pure product or pure chemical over impure chemical. So if you know how pure your chemical is, you just gotta divide it by how impure your chemical is. Now don't forget, because these are all percentages, you're always going to multiply these by 100% to get the percentage. Same with this one. So in this case, again, we want to solve. So step one still is we solve our calculations using stoichiometry still. So we want to always get from one thing to the other. So we want to use our calculations to solve first. So, what does that mean? Well, what that means is, in this case for purity, again, if given a reactant and you solved all the way to a product, you just solved for your impure. And if given a product and you are asked to convert back to how much you need of this reactant, you just solve for your pure. So you might notice that if you're going from reactant to product, you're always solving for your denominator. If you're going from a product to a reactant, you're always solving for your numerator. And it's always this case. Now here's a little thing you want to write down to make sure that this is the case. You gotta make sure that your percentage should never be below 0%, aka cannot be negative percentage, or over 100%. Because if you're over 100%, then there's no way that's possible, which means that there must be some impurities in your product. So what are the steps of solving percentage yield and percentage purity? Well, the biggest thing you just gotta know is perform stoichiometric calculations as before. Just apply the percentage at the end. And then apply percentage at the end. So what are some things we should be careful about? Well, some of the things we need to be careful about is when you are performing these, the amount of reactants you need in the real world is going to usually more than what the calculations ask for. So in real world, you will need more reactants due to yield and purity. That should be an and sign. And so that is why it's really important that that is the case. So sometimes we are going to need more reactants because of this. And to find the amount you need, you divide your theoretical yield by your percentage yield. Or to find actual pure substance, again, you divide your percentage purity to find how much product you actually need. So this just means, what do you do if you were given percentage and you want to find your one of these. If you want to find your peer or in-peer, or your actual or theoretical. So let's practice these using these examples. Let's look at the first example here. The first example here is asking, what is when 16.7 grams of CH4 reacts with excess O2? Well, if that right away says excess O2, that means CH4 is your limiting right away. So you don't have to worry about limiting excess reagents. A total of 30.5 grams of CO2 is produced. So here, first of all, we need a balanced reaction, or else we can't do stoichiometric calculations. So we have CH4 react with O2 will always form, because of the combustion reaction, CO2 plus H2O. And now we need to balance this, where we put a 2 in front of this and a 2 in front of this to balance it out. So, when you are given 16.7 grams of CH4, which is right here, that's a reactant. You find that 30.5 grams of CO2 is produced. That's a product. So if you use 16.7 grams of CH4, that's a reactant, and you're converting to a product. So every solve at the end is going to be your theoretical yield, because this 30.5 grams is actually your actual yield, because it's from the actual experiment. So in this case, let's go solve this. 16.7 grams of CH4. We want to get to moles, because we want to convert to CO2. So we know 1 mole of CH4. What's the molar mass of CH4? The molar mass of CH4, well, we have carbons 12 plus 4, that's 16.0 grams. So our grams will cancel out. Now we want to cross the mole bridge. So it's 1 mole of CO2 over 1 mole of CH4. And now we can see our moles of CH4 also cancel out. Our last thing is to get to mass of CO2, which we see is going to be 12 plus 32. That's 44.0 grams. That's the molar mass of CO2 per 1 mole of CO2. So now we're going to find what mass of CO2 theoretically should we have calculated. So if you punch it in your calculator, 16.7 divided by 16 times 1 divided by 1 times 44. We should have theoretically found that the mass should have been 45.925 grams. 45.925 grams. This is your theoretical. Now again, why is it theoretical? It's theoretical because I converted my CH4, which is a reactant, into CO2, which is a product. And when we go from reactant to product, according to what we stated here, when we're going from reactant to product, if we found it right here, reactant to product, we're calculating for our theoretical yield. If we do it backwards, we're calculating our product to reactant, we're calculating our actual yield. Okay, so in this case, that's what we have. We have our theoretical yield. Where's our actual yield? Our actual yield is 30.5, because that's how much is created in our reaction. So what we have is we have a formula to calculate percentage yield. Percentage yield is equal to your actual yield over your theoretical yield, which I'll abbreviate as act over theo. So this will mean that you have 30.5 grams divided by 45.925 grams. What is that percentage? Well, 30.5 divided by 45.925 is going to give you, times by 100%, around 66.4%. So the yield is 66.4%. That means you would have expected to have produced, from calculation, 45.925 grams, but in reality, actually, you only produced 30.5 grams, which is why it's 66.4%. Okay, what if I went instead, I didn't do all this calculation, instead I started with 30.5 grams of CO2 and I converted it to CH4. Well, if I'm doing it backwards this time, I'll show you that you're going to get the same percentage yield. So if you want to write this on a separate piece of paper, you can. So what I'm telling you here is if I were to convert, instead of my CH4, I'm converting 30.5 grams of CO2 this time. And I want to now convert that CO2 into CH4. Well, if I'm going from a product to a reactant, this time whatever I calculate will be my actual yield. So let's see this. So I have grams of CO2, I want to get to moles of CO2. To get to moles, find the molar mass, and that's 44.0 grams. So our grams will cancel out. Our next step is, this is moles of CO2, get to moles of CH4. That is 1 mole over 1 mole because of the mole ratio. So again, that will cancel out. Our last step is to find the mass of CH4, which is 16 grams over 1 mole of CH4. And that will finally cancel out. So here, if we calculate it this time, we will see that 30.5 divided by 44 times 16, we will get expected in actual of 11.09 grams of CH4 actual. Now why is this actual again? Because I'm converting a product this time to my reactant. And when you convert from a product to a reactant, you're finding the actual yield. So that is how, if you look at this, we did this question once. I want to show you that you're going to get the same percentage this time again. So how, if actually we only got 11.09 grams, but theoretically we started with 16.7 grams, what is percentage here? Well, in this case, the percentage is going to be hopefully the same. So if we do 11, so again, percentage yield is equal to actual over theoretical. Well, this time, this is my actual. So I'm going to put, in this case, 11.09 grams divided by 16.7 grams. If I punch this in my calculator, divided by 16.7 grams, I should get 66. So if I multiply this by this 100, you should see that I still get the same percentage. It's 66.4%. So what I'm trying to show you here is it doesn't matter which chemical you use. As long as you know what I solve, is it going to be my actual or is it going to be my theoretical? So the percentages are exactly the same, 66.4%. So that's why you got to be careful. Okay, if I'm starting with a reactant and I convert to a product, I just convert for my theoretical. If I go from a product to a reactant, I found my actual. So let's try the next question. Example number 2 is asking, what mass of K2CO3 is produced? So K2CO3 is this chemical right here. Is produced when 1.6 grams of KO2 is reacted. So this time I'm looking at this chemical. So I'm converting 1.6 grams to this chemical. With an excess of CO2, which means we don't have to do limit excess, if the reaction this time has a 50% yield, that means they're giving the percentage yield. Well, if I'm going from 1.6 grams of KO2 to a product, so if I'm going from this to this, I'm going from reactant to product, I will solve for my theoretical. So here you can see what mass of K2CO3 is produced. Well, what is it going to be actually produced? So let's find out. So if I have 1.60 grams times, this time, the molar mass of KO2, the molar mass of KO2, if you look at the periodic table, K is 39.1 plus O2 is 32 of them, so we have 71.1. 71.1 grams. So now you see our grams cancels out. My next step is now to convert and cross the mole bridge. The mole ratio here is 2 to 4. So 2 moles of K2Cl3 over 4 moles of Kl2. As you see here again, our moles of Kl2 cancels out. My last step is now to find the mass of K2Cl3 because I need to convert to the mass. Well, what is the molar mass of K2Cl3? Let's find out. K2 means it's 39.1 times 2. That's 2 potassium mass plus 1 carbon, which is 12, plus 3 oxygens, which is 48. I will get 138.2. So it's 138.2 grams per 1 mole of K2Cl3. And that should cancel out my moles of K2Cl3. So I just calculate for what mass I'm expecting to get theoretically. So if I multiply this and find out what it is, 1.2 divided by 71.1 times by 2 divided by 4 times by 138.2. And I expect to get 1.555. So in this case, it should be 1.555 grams expected, which is your, this time it's theoretical still because I went from a reactant to a product. Okay, so what happens here now? Well, in this case, our calculations is to find yield is percentage yield is equal to actual over theoretical. Well, our percentage yield is 50%. Now remember, 50% is not 50, it's 0.5. So it's going to be 0.5 is equal to your actual, which we don't know yet, over 1.555 grams. So what I do is I take this number, I don't round on my calculator yet, and multiply by 0.5. And I should expect an actual yield is equal to 0.777 triple sevens, 0.777 grams actually. So that means from this reaction here, I will actually only produce 0.777 grams of K2Cl3 from 1.6 grams of Kl2. I won't actually produce 1.555 grams because this thing has a 50% yield. If it had 100% yield, then you would have produced 1.555 grams of K2Cl3. Because it only has a 50% yield, you only produce 0.777 grams. So just remember, always in these examples, you could pause the video and try on your own. But if not, I'm going to continue on with these examples. What mass of CuO, copper oxide, so this should be copper 2 oxide, is required to make 15 grams of copper according to the reaction 2NH3 plus 3CuO gives you N2 plus 3Cu plus 3H2O if the reaction has 60% yield. Okay, so I am given 15 grams of copper, and I'm trying to find what mass of CuO, which is a reactant. So I'm converting a product this time to a reactant. Well, according to my strategy, I'm going to find my actual yield if I do that. Actually what I need. So in this case, I'm going to start with 15.0 grams of copper. And I will multiply by 1 mole of copper over the molar mass of copper, which, if you look at your periodic table, is 63.5. Okay, because that will cancel your mass. Our next step is now to cross the mole bridge, which is going to be 3 moles of copper oxide over 3 moles of copper. So that will cancel your copper. Your last step is to now find the mass of CuO. Well, what is the molar mass of CuO? Well, if copper itself is 63.5, oxygen is 16, you're going to end up with a molar mass of 79.5 grams. If you don't believe me, 63.5 plus 16 is 79.5 over 1 mole of CuO. So as you see, your moles of CuO will cancel out. So I'm just going to solve for my mass of copper oxide that I am actually going to need, but I need to find how much I need theoretically. Okay. So right now I have 15 divided by 63.5 times by 3 divided by 3, which means really just times by 1, times by 79.5. And I'm going to have a mass of 18.78. 18.78. Oops, that should be an 8. 18.78 grams. And so this should be the mass of CuO that I'm going to actually need. But I'm actually going to need a bit more than that because my yield is only 60%. So in this case, what this means is if my reaction was 100% yield, I would need just 18.78 grams of CuO to create 15 grams of copper. But because my yield is 60%, I actually will need more than 18.78 grams. How many more? Well, let's see. So if I apply my percentage yield calculation, yield is equal to actual over theoretical. What I'm going to get is percentage yield, in this case is 60%, so I should plug this in as 0, oops, shouldn't have done that, 0.6 is equal to 18.78 grams over theoretical. How do you solve for this? Well, there's a little shortcut if you know your algebra is if you run this, you just swap these two. So you're going to get 18.78 divided by 0.6 is equal to your theoretical. What is it going to be? Well, divide this number by 0.6 and you're going to get 31.3 grams. 31.3 grams, but I'm going to ignore this number as a sig fig just because it will actually be 1 sig fig, and I'm going to leave it as 3 sig figs. So this is what you're going to need theoretically. What that means is you're going to need, in this question, you're going to need 31.3 grams of your copper oxide to form 15 grams of copper because of the 60% yield. If you had 100% yield, then that is the copper oxide you'll need. But because 60% yield, you'll need 31.3 grams to make 15 grams of copper. Alright, what if we do impurity questions? Well, remember, impurity questions are exactly the same questions, just different terms. So let's see what we have. If 100 grams of iron 2 oxide produces 15.6 grams of pure iron, according to this reaction, what is the percentage purity of iron 2 oxide? So we want to convert this iron here into iron oxide. Okay, let's try it out. So we have 15.6 grams of iron. Iron is right here. So we are starting with a product. Fe, iron, is a product, and we're going to convert it to FeO, which is a reactant. So we multiply this by 1 mole of iron over the molar mass of iron is 55.8. 55.8 grams. So that is going to cancel out my grams. My next stage is now to cross the mole bridge, which is 2 moles of FeO over 2 moles of Fe. So that will cancel out my moles of iron. And my last step now is to multiply by the molar mass of FeO. The molar mass of FeO, if iron is 55.8, I add an extra oxygen, which is 16. I'm going to get 71.8 as a molar mass. 71.8 grams per 1 mole of FeO. And that is going to cancel my moles of FeO. So I'm going to find what is going to be the mass of my FeO that is actually, in this case, my pure. So 15.6 divided by 55.8 times 71.8, I'm going to get 20.07. So 20.07 grams. Because I went from my product to a reactant, I just found my peer. That means of this 100 grams of iron 2 oxide, only 20.07 grams of it is FeO. The other 80 or so grams is not pure. That's what we talk about when we talk about purity. So if we were to calculate the percentage purity here, percentage purity is equal to pure over impure. So we found our pure. We know what our impure FeO is. Well, what's our percentage purity? So in this case, it's 20.07 grams divided by 100 grams. This is going to lead you to find that your percentage purity is 20.1% pure. That means this iron 2 oxide that you started with in this reaction, only 20.1% of it is pure FeO. Because if it was anything higher than that, you would have expected a way higher iron getting produced. So that is showing you that these type of questions are exactly the same type of questions. So let's look at the next question. What mass of impure zinc metal having a purity of 85% is required to produce 1 liter of hydrogen gas at STP according to this reaction? Okay, so you're trying to find the mass of zinc metal, which is right here. But you're given your hydrogen already. So you're going to go from a product to a reactant. So you're trying to find the mass of impure zinc this time. So in this case, because you're given your product, it's 1 liter of hydrogen gas. Well, because it's STP, you could use STP to solve 1 mole of hydrogen gas over 22.7 liters. That will cancel your liters. Then you cross the mole bridge. In this case, it's 1 to 1. 1 mole of zinc over 1 mole of hydrogen. And last but not least, find the molar mass of zinc to find the mass of zinc you're going to create. So in this case, what is the molar mass of zinc? Molar mass of zinc is 65.4. 65.4 grams over 1 mole of zinc. So that will cancel your remainder. So you're left with just mass. So if I were to put this in my calculator, I will find 1 liter divided by 22.7 times by 65.4. I will expect to get a mass of 2.881. So 2.881 grams of zinc. Now, did I just find my pure zinc or my impure zinc? Well, according to when I previously went over this, you would remember that if I convert from a product to a reactant, I solve for my pure amount. What is my pure amount of zinc? So this is pure. Well, how do you find the mass of impure zinc? Well, you have your purity, you have your pure mass, you could use your calculation to solve for your impure. So in this case, percentage purity is equal to pure over impure. Well, if it's 85%, that's 0.85 is equal to 2.881 grams over impure. Using what we learned previously, if you want to solve for x, you could swap these two. So that leads you to have impure is equal to 2.881 over 0.85. That will give you a value of 3.39. But if I were around, in this case, 2 sig figs, because 85% is 2 sig figs, it'll be 3.4 grams. And this is the impure zinc we're going to have. So if I wanted to produce 1 liter of hydrogen gas, If I had pure 100% zinc, I would only have needed 2.881 grams. But because I have impure zinc, I need 3.4 grams to make it produce 1 liter of hydrogen gas. Alright, our last question. Our last question here is, calculate the mass of Mg3PO42 that will be formed from the reaction of 15 grams of MgOH if it has a purity of 85%. So in this case, we are given MgOH. So we're given a reactant. And we want to find the product that will be formed. Alright, so this time we're going to solve for our impure. So 15.0 grams times 1 mole of MgOH2 over, what's the molar mass of magnesium hydroxide? Well, if we look at magnesium hydroxide, magnesium is 24.3 plus 2 OHs. Well, if 1 OH, 16 plus 1, that's 1 OH, that's 17. That means I add to it becoming 34, so it's 58.3. The molar mass of magnesium hydroxide is 58.3 grams. So my grams will cancel out. My next step is now to cross the mole bridge. In this case, it is 1 mole of magnesium phosphate over 3 moles of magnesium hydroxide. Okay, so that should cancel out my moles of magnesium hydroxide. My last step is to find what is the molar mass of magnesium phosphate. Well, I have 3 magnesiums, so if each magnesium is 24.3, I multiply that by 3. I have 72.9 grams of magnesium per mole. I add that to 2 phosphates, so 31 plus 31. And I add that to, in this case, there's 8 oxygens. So I add that to 8 times 16 equals 262.9. So 262.9 grams per 1 mole of magnesium phosphate. And that will cancel my magnesium phosphate. So what you have here is some mass. Now what is that mass? Let's go find out. 15 divided by 58.3 divided by 3 times by 262.9. I get a mass of 22.547. 22.547 grams. Now is this my pure amount or my impure amount? Well, I went from a reactant to solve to a product. In this case, because of that, this is my impure amount. This is how much of Mg PO4 I would produce and other crap with it. But if it only has 85% purity, what is the actual mass of Mg3PO4 I will produce? Well, percentage purity is equal to pure over impure, which means that 85% is 0.85 is equal to, in this case, pure over 22.547 grams. Multiply both sides by 22.547 grams, and you're going to get a pure amount of, times this by 0.85, you're going to get a pure amount of 19.2 grams. If I do, in this case, 3 sig figs. 19, or in this case, 2 sig figs will be 19 grams of pure magnesium phosphate. So that is the purity of the magnesium phosphate. Only of this 22.547 grams of it, only 19 of it is magnesium phosphate. The other 3.5 grams is something impure to it. So your homework for this section is number 33 to 38. Now this homework is going to practice a lot of purity questions and impure questions. So make sure you get a lot of practice from this. Now, as always, make sure you keep yourself safe and healthy, and I'll see you soon.